Now we're going to go to our next exciting talk, which is going to be Amina Helmi, and she is going to describe for us new views on the galaxy from the Gaia space mission.
Hi, good morning. It's can you hear me?
Yes, we can hear you.
Great. So let me share my screen. Let me go to the first slides and set up the show. I'm actually in Europe, so it's afternoon here, but I understand we're spanning a large range of different time zones. And it's my great pleasure to be talking about sharing with you new views on the Milky Way from the Gaia mission. As you might know, Gaia is a European Space Agency satellite that was launched at the end of 2013 and has been scanning the sky since 2014. And just about 2 years ago, a revolution was triggered by the release of the second data release from Gaia. And it's really revolutionized the way we look at the Milky Way. So Gaia is a mission that scans the sky. It observes basically every object that's brighter than a certain magnitude or certain brightness, which is around 20 for the astronomers that think in magnitudes. And so by observing every object on the sky, that it ends up with a catalog that has of the order of 1.7 billion sources. So what you can see here is because this Gaia basically scans, as it scans, it not only measures the positions of the individual sources, but as it does this over time, many times throughout the year, it actually measures how much the sources have been moving on the sky. So it actually measures how stars, every object on the sky that's sufficiently bright, has moved over the time span. And therefore, it gives us a map of not only where the stars are, but also of how they have moved on the sky. And this is what we call the proper motions. It also gives us the distance to the sources, so that it gives us the 3D position of a source. And for a subset of the stars, of these 1.7 billion sources, we have 7 million sources at this point in time for which there is a spectrum. And we've therefore been able to measure how the object moves along the line of sight from the Doppler shift. For all of these objects, what we also have is their brightness in different bands, and that allows us to infer different astrophysical properties for the stars, such as, for example, the temperature. And with a data set like this, you can make beautiful images of the Milky Way. But I think that's not the most exciting bit, at least for me scientifically, but it's the fact that for all of these sources, we can actually measure, we see them move, as you can see in this animation. And because we are seeing stars move through the Milky Way, we actually see where basically these movements are unraveling the forces that are driving those motions. So with data sets like this, we can, for example, ask ourselves, what is the nature of dark matter and what is the nature of gravity? Or do we need to think of gravity in a different way? Because the motions of stars are unraveling the gravitational field in the Milky Way. So with a data set that's huge and so rich and of such high quality, there's a variety of science that one can do that goes from the smallest scales of, say, the solar system, the nearest object to us, to the farthest objects from us, which are these, for example, quasars, going through how stars form in the Milky Way, the dynamics of the different components of the Milky Way, to the distribution of dark matter around it. So there's a lot of science that one can do, and this is why this mission has been is so successful, actually. And if you follow, for example, the archive and you follow AstroPH, typically there are 2 papers per day using Gaia data. So it's extremely exciting and a high impact mission. But really the reason Gaia was built, or one of the key questions, was to address this question of how did our galaxy come to be the way it is? So as you can see in this image produced by Gaia, the Milky Way, I hope you can see my cursor. The Milky Way has a thin disk where most of the stars are, and where stars basically move around on circular orbits. It has a central component, the bulge, the bar. It has a stellar halo, which is more diffuse, and it has a thick disk. And so the stars are not only distributed differently in these different components, stars move differently in the components. So in the thin disk, as I was saying, they follow circular orbits. In the halo, they follow very elongated orbits that take them very far out from the center of the galaxy. But not just that, the stars themselves are different. So for example, the stars that we see in the halo of our galaxy are basically as old as the universe itself. And they are also very pristine in terms of the chemical composition that they have. And so effectively, these stars have witnessed how the Milky Way was put together. And so they're extremely useful for unraveling the history of the galaxy. So that brings me to the next point, which is that we can actually use stars to do some kind of archaeology to try to figure out how the Milky Way was put together. We have a theory for formation of galaxies in the cosmological model. And this is what you see here on the right is a series of snapshots from a simulation of the formation of a galaxy like the Milky Way. And what you see basically is initially you have a lot of small galaxies. They get together through the action of gravity, they merge, they produce larger and larger systems. And by the end of the day, what you have is a disk galaxy in the center formed by stars that formed in the Milky Way itself, as it were. And the stars that are around this disk basically formed in these different small galaxies that we see in the top left panel. And so the question really is this the way the Milky Way formed? Is this the way the stellar halo formed? And if so, how many mergers did the Milky Way experience? What were the properties of these galaxies? Remember, we're actually looking back in time. So we learned about the properties of galaxies that are extremely distant, that are basically were present in the early universe. The reason we can do this kind of work is, as I was saying, is that stars are like fossils. So stars remember where they come from, and they do this in many different ways. One of them is that in their motions, so you can see, for example, in the bottom left panel, you can see structures here, and the stars in the structures are really moving together through space. So in their motions, we can tell origin. In their ages, we learn when stars were born. And from the chemical composition, actually stars retain in the atmospheres the chemical imprints of the cloud in which they're formed, of the system in which they're formed. And this doesn't change with time. And so by looking at stars that are very pristine with a low, for example, iron abundance, we really are going back in time, as it were, to the early universe, to the first stars. So with all of this information, we can use the stars to reconstruct how the Milky Way was put together. And as I was saying, basically the stellar halo plays a critical role here, because it's the place where most of the debris from all these building blocks is deposited. So if we're trying to figure out how the Milky Way was put together, then we need a sample of halo stars. So that brings me to a few highlights that I wanted to share with you from the Gaia mission. And this is a biased set of highlights. I mean, as I was saying, Gaia has produced a huge amount of data and a large amount of papers, and it's not always easy to keep up with the literature. And it's just so very broad, astrophysically speaking. So what I decided to do is to describe 3 different results from Gaia, which are the ones that to some extent I like the most. 2 of the results I've been involved in, but the third one, so these are these 2 on the halo and the disk of our galaxy, and the third one, which is on streams. This is work that has been led by Anna Bonazza and collaborators in the US that I think is just so beautiful that I wanted to share it with you as well. So let me take you through the first highlight. So what I'm going to be discussing is the halo. And as I was saying, the halo is really for us like a treasure trove. As I described just now, what we think is that the halo is formed from the debris of many different galaxies. And if you take a simulation and you take all of the different galaxies and you take the stars in these galaxies and give them each of them a different color, then basically you end up with a halo that has a lot of substructure from the different objects. So the green stars come from one object, the purple ones come from a different one. And this substructure you would see spatially. And in fact, this is what we see when we take observations of stars around our galaxy. We do see lots of structure, like large overdensities, streams, narrower streams, sharp overdensities. And all of these indicate that at least the outer, the regions that are farther away from the center of the galaxy were indeed formed by accretion. But what we don't know is whether the very center where all of the debris overlaps and where we have the highest density of stars actually really also formed in this way. And to figure that out, what we need is motions. And this is where Gaia was absolutely critical. So then the question is, how do we actually find merger debris in the inner regions of the galaxy? So what I'm going to show you now is a movie of how a small galaxy gets torn apart because of tidal forces. These are the red particles in this movie. And as this satellite orbits around the Milky Way, the stars follow that original orbit. But very quickly, what you see is that there's very little information in the spatial distribution of the stars. But if you look at any given point, any given location in the galaxy, what you see is that the stars are really moving together through space. And so this is a snapshot of that. So you have, say, streams of stars, and then if you take what would be the location of the star, the sun, and you take a small volume around it, and you would look at what the stars are doing in velocity space, then you would basically see one group of stars moving in this direction and another group of stars moving in this direction. So if you plot velocities, then you see one clump and you see a second clump of stars. Now, one way of thinking about a satellite is not just thinking in terms of position or velocity, but because these stars were clumped together initially, they actually had very similar energy, so kinetic and potential energy, and very similar angular momentum. So this is what is shown in this diagram, angular momentum and energy. So they define a single clump initially. Now, if energy and angular momentum are integrals of motion, they're conserved quantities, they don't change in time. So even if after, if you take this simulation and you look after all of its evolution, you would still see a clump in this space. So if we have going back to our image, if we have a halo constructed from mergers, and we don't really have these stars don't come with flags telling us from which object they originate, we can look at the velocities and find individual structures, but we can also look at the space of integrals of motion of conserved quantities, and each one of these galaxies will correspond to a clump in this space. And you can see that even if you didn't have the color coding, you would be able to see the structure in this space. So it's extremely exciting. And we had this tool ready already in the year 2000. So we had to wait until 2018 to be able to do this test, but finally the Gaia data arrived. And so what we did is to select a sample of halo stars near the sun. And the way we select halo stars is by looking at stars that are really moving very differently from the disk. So what you can actually see here is in the top right is you see the disk of the galaxy. I just want to define a reference system here. The sun is located here. This is the galactic center. And stars have a velocity in the direction of rotation of the disk that we call v phi or vy. They have a velocity perpendicular to the disk, which is the z velocity, and they have a component of the velocity in the radial direction. And so what you're after when you look at the halo is really stars that move very differently from the disk. So the majority of the stars we live in a disk galaxy will move like the disk. And so in this diagram of Vy and these two velocity components, Vy is rotation. So most of the stars are actually here moving like the disk itself. And the halo would be the stars located beyond this boundary, this red curve. Right, so this would be the halo stars. Now, what's striking about this picture is that the distribution, the kinematic distribution of the stars is definitely not smooth. This is not a Gaussian distribution. What you clearly see is a strong contribution of the thick disk, of the tail of the disk at very low velocities, right? This is the thick disk. Then you see a big blob here, some substructure here, and an arc here. You can plot other velocity components, again, rotation, again, the radial direction, or rotation against velocity, and you begin to see small clumps, such as those marked here. If you look at energy and angular momentum, you see the large structure again, the blob here, the disk, the tail of the disk here, and some small overdensities. So this picture doesn't look like the simulations I showed you with the little clumps everywhere. There are some clumps, but the thing that's most striking here is this blob, which actually, if you pay attention, it's actually counter-rotating. So most of the stars in the disk, they go clockwise, but this feature has an average velocity of rotation in the other direction. So it seems like basically, if you discount the thick disk, basically the halo is actually rotating in the opposite sense as the vast majority of the stars in the disk. So that's very surprising. So we decided to take a closer look at these stars that are located in this structure here, in that blob. So this is what's shown here. So these are the stars that are selected in that case. And then what happened is that we remember we had a simulation in-house of the merger of a disk with another large galaxy. And that simulation is shown in the right panel. And what is shown here, the color coding here corresponds to stars. The stars here in this structure are the stars from the satellite galaxy that merges with the pre-existing disk, which is in black. So the resemblance is rather strong. This corresponds to a merger of 5:1 mass ratio. It tells us this feature here that we see this arc here. We see it on this side. That tells us the shape, the impact of the encounter. And the fact that the mean velocity is negative tells us that the encounter was retrograde. Now, the resemblance to a simulation doesn't actually tell you that the data, it's not proof that actually what we are seeing as the blob is an accretive galaxy. So then what we decided to do was to look at the chemistry of the stars. And so I want to spend a bit of time explaining, the chemistry here. So what I'm plotting here are alpha abundances over iron. Alpha element abundances, alpha elements are elements like calcium, titanium, magnesium, and these are produced in very massive stars that explode as supernovae, we'll call supernovae type 2. Iron is also produced by supernovae type 2. But iron is also produced by the mergers of stars in supernovae type 1a. And so what you expect, which have a longer time scale for evolution. And so what you expect in a given system is that actually alpha to iron will stay flat and then go down as time goes by. And so when we looked at the chemistry of the stars, what we found is basically the thick disk, the thin disk, the thick disk. And then we found that the stars in the blob followed a separate sequence from that of the stars in either of the components as we knew them. So this separate sequence actually has a lower alpha over iron abundance than the thick disk. And the thick disk stars formed in situ because they are on such circular orbits. So actually this tells us, because the alpha over iron always decreases with time, but cannot be lower than that of stars formed in the Milky Way, that actually tells us that the stars in this blob were formed elsewhere. And from the characteristics of the sequence, we can actually tell in which kind of object. And it's an object like, for example, the Large Magellanic Cloud. For those who you've heard of this galaxy, but that was there, a long time ago. Because in fact, we can measure the ages of the stars that are present that have the chemistry. And for these stars, we can tell the stars with the highest iron would be the youngest stars that formed, the last generation of stars that formed in the system. And these are of the order of 10 billion years old stars. What we also know is that at the time, the Milky Way already had a disk, because the stars of similar abundance at that metallicity are actually older. So actually what happened is that at the time this big galaxy came in, there was a disk in the Milky Way, and this disk, because the merger was so massive, actually led to the formation of the thick disk as we know it, probably by puffing it up, but also by leading to a lot of star formation in the disk. And so this is a movie that actually we had in-house, but turned out to be very useful to show how that event happened and what happens when a large galaxy impacts another galaxy like the Milky Way at that time. So 10 billion years ago, something like this happened. We gave the name to this other galaxy, Gaia-Enceladus, and if you want to ask me later on, I'll be happy to tell you why I think this name was meant to be. So this is what we know now, therefore, is that the halo basically stems from the merger of these two galaxies. But what we also have is other substructures. We've identified them. We're in the process of trying to characterize them and to really do archaeology, because by characterizing these systems, we then learn about how galaxies looked like in the early universe. So 10 gigayears, 10 billion years ago, and even beyond that. So let me now go to another component, the disk of the galaxy.
You'll need to unlock your iPhone first.
Most of the stars, as I was saying, in the Milky Way are in the disk. And so what we did is to look at the kinematics of stars near the sun. And what I'm showing here are the velocity distribution of the stars in the different components. And one of the things you see, so this is rotation, this is again velocity in the galactic plane, this is vertical velocity. And so what you see is a huge amount of substructure. You actually see arcs, you see shells, you see lots of features. And this bit here was actually known to be due to the galactic bar. It's a resonance with a structure that rotates, but the rest was not known. And so once you look, actually, you see shells, you actually think, okay, we should look at phase space diagrams. And so what I've showing here is the Z component versus the height above the galactic plane. And if you just make a plot that shows the quality of the data, you can actually see this Snell shell. And this is a signature of phase mixing that comes up in many different fields. And the reason we're seeing this is that the disk was perturbed out of equilibrium some time ago. And because it was perturbed, actually, if you let that perturbation evolve, it was slightly kicked by something, and this phase mixing then leads to the formation of this spiral that we see. So what this tells us actually is that the disk at some point, which we can tell was about 500 million years ago, was out of equilibrium. The object that probably caused this is the Sagittarius dwarf galaxy, which is a small galaxy that we thought was totally irrelevant for the dynamics of the disk. But basically induced a small perturbation, but not that small that we couldn't measure it. And so we can measure this now. And what this actually tells us is that the Milky Way is a dynamic entity, that we cannot treat galaxies as island universe and model them dynamically as time-independent systems. And this has a direct impact on the determination of the dark matter density near the sun, because it's always been based so far on modeling the Milky Way as a static system. So there needs to be more work done taking into account the fact that it's not time independent. So let me go quickly to my last set of slides on the streams, which I think is extremely exciting work. So as I was saying, as a galaxy, as you saw in the movie, as a galaxy or a small system gets perturbed, this gives rise to streams. And the reason streams are interesting is because you can ask the question of whether this picture that the Milky Way sits in a dark matter halo made of cool dark matter is correct. Because if that were the case, the halo would be filled with these clumps of dark matter that would be orbiting around the Milky Way. We don't see so many clumps. We actually see a few, say, tens of satellite galaxies, but we don't see hundreds of thousands. We see basically this. We don't really see the dark matter. So the idea will be to try to see if we can have an experiment to unravel, to shed light on this substructure. And what you can imagine is if stars move through this distribution of mass, they will move as in a bumpy road. And so if you take a stream, because it's a very coherent structure, and you hit it with a subhalo, that produces a gap in the stream, that produces perturbations in the stream that are visible because of the coldness of the system. So people have been looking at streams for a while. And before Gaia, this was the picture that we had of this very long, thin stream known as GD1. And you can sort of see that there are gaps in the distribution of stars, but you can also see that the background noise is very, very high. So it's very hard to say, okay, this is significant. But with Gaia, you can basically do a lot better because you can clean the background using the motions of the stars. And one of the things that turned out is that we see indeed a lot of structure in the stream. This is quantified here in the surface density. You see gaps, but you see also something like that's become known as the spur. If you pay a bit of more attention to the spur and you try to model it, you can actually produce a structure like this. So this is the data, this is a model, this is the work from Bonazza and collaborators. You can model this with by an encounter with this stream that happened 500 million years ago, roughly, with an object of small mass, 5 times 10 to the 6 solar masses. Now, this is a very interesting mass regime because this is where you might expect to have lots of clumps of dark matter orbiting in the halo of the Milky Way if dark matter was cold. And in fact, the region of parameter space that's allowed, that produces spurs like this is here. this is the region that would be allowed for cold dark matter. This is the region occupied by globular clusters, which we can see. And not only can we see them, we can actually measure how they move. We have measured with Gaia how they move through space. And none of the globular clusters that we know actually come close enough to this stream to induce a perturbation like the one we see. So the bottom line is that this perturbation could definitely be due, at least is due to an encounter with an unknown object. And follow-up work shows that it's possible to more or less pin down the location or the orbit of that object to be on the plane of the Sagittarius dwarf galaxy. So this is very exciting because potentially this could be, a dark subhalo. So that brings me to my last slide on the summary. I hope that in this quick talk I gave you could convey the excitement of the Gaia mission, and that's truly causing a revolution in the field because of the amount of data, because of the quality of the data. Things to remember are that the halo is largely the result of the accretion of one massive galaxy, similar to the Magellanic Clouds. This has implications of what is the dark matter content near the sun. We find several other structures present in the halo of the Milky Way. There's more discoveries to be made. The other thing to remember is that galaxies are not island universe, and that our constraints on the local dark matter density need to be revised because of the time varying potential of the Milky Way. And I think what's extremely exciting is the prospect of being able to constrain the properties of dark matter using streams, and the fact that maybe we have seen dark matter subhalo. And with that, I'd like to stop. Thank you.
Thank you so much for your lovely talk. And we do have a couple questions in the chat window that I'd like to share with you now. Brett asks, would the backwards rotation of the halo have any effect on annual modulations of dark matter detections? Does halo star motion trace halo dark matter motion?
Yes, so there is, I think to zero order, we can assume that the stellar halo will be a tracer of the dark matter halo. It's not one-to-one because the stars are more compact, they are distributed in a more compact fashion. But to zero order, they should trace each other. And therefore, my guess is that it should have an impact. It's just we have not yet, but it's in the planning to actually do modeling on the annual modulation signal, and also on the velocity distribution also for different dark matter detection experiments of what you would expect to see near the sun. Yes.
Thank you. And one last question from Felipe. In spite of the retrograde sense of motion, is the modulus of the velocity the same or close to that of the typical disk velocity?
So on average, the halo is at rest, right? So the sun moves at about 220, 230 kilometers a second around the center of the galaxy, and the halo would be at rest with respect to the center of the galaxy on average. I mean, it's slightly retrograde as we see from this component, but what we see is that you shouldn't model these as a Gaussian distribution. I think that's the punchline from what the stars are telling us.
One last question just came in. This is from Matthew. Is it safe to say Mond-like theories are extra dead now?
Okay, this has not been done. I don't think this conclusion has yet been reached with Gaia data, because I don't think people have started to model Gaia data in the context of Mond. But what we know from the streams, from their constraints, is, for example, from the shape of the dark matter halo around the Milky Way, it tends to be elongated, perpendicular to the plane of the Milky Way, and you can't produce that with a Mond because you would expect that that would produce a halo or the equivalent of a halo that's spherical. So the acceleration is just not of the right, in the right sense.